All right, can we continue? We need to finish. I mean the example by today, and next week we will continue a little bit on another example, and if possible, we need to go to chapter 6 as soon as possible, because that one is very important, and you need to understand that, and you need time to practice. Okay. So can we continue?
Yes, Ratu.
Uh, Hold on. June want to have the Verilog code. Yes, I will share the code. But actually the code is the same as the one in the lecture note. I think exactly the same. Mm, yeah, here is the code. You can use this one. Copy and paste. You can get the result. Try to do that. Cannot.
Okay, doctor.
Yeah, it is the same actually. Okay, now we want to do this, and this is the sequence. Yeah. First, we want to transfer the data from the input here, data in, into rack 1, and from rack 1 into rack 2, and from rack 2 into rack 3. So, and that this thing cannot be done at the same time, because again we share the same bus. All right, and we cannot connect or access or use this bus uh, at the same time, right? So we need to have or separate the operation. So we can use state diagram actually to represent the process. So it will be something like this. So we can have a state diagram where we can have S0. What we will do is reg1 data in. Okay, S0. We do this, and this is from reset, and we start. And the next one, we can have S1, where what we do is to transfer the data from rack 1 to rack 2. And the last one can be this. Rack 3, rack 2, rack 2, and this is S2. And the transition of the state is not depend on any input, but only depend on the clock, because this must be done after this, and this must be done after this. Yeah, we're not waiting for any input, means that our this is state diagram, and of course the state diagram will represent the finite state machine, and this finite state machine have no any input except the clock. All right, because we will not depend on any input for this state to change to the next state. only depend on the clock signal, meaning that if we have the clock signal, yes, so if it is positive edge, so the first cycle we will be in as 0, and immediately at the next clock cycle we will be in as 1, and the next clock cycle will be in as 2 automatically, right? And what we want to do is in S0 we want to get data in into R1. So how to do that? So we need to look at our data path. In this case, this is our data path. Yeah. So to do that, what we need to do is that in state S0, what we want is that SEL must be equal to 1, right? Means that the output of this finite state machine is SEL1, and also LD1 must be equal to 1 in order to load the data into the register. All right. So the output of our FSM, if this is our FSM, so of course we have the clock and we have the reset. The output will be SEL1 as LD1, and also actually LD2 for this one, because we want to load the data into LD2. So LD2 must be the output of the finite state machine also, LD2, and actually we have more. We have LD3, also the output. We have SEL2, and of course SEL2 is 2-bit. So these are the output of this finite state machine. And at S0, LD1 must be 1, SEL must be 1, and the others must be 0, not active, all right, or don't care. But in design, we cannot put don't care. Yeah, in control signal, we have to put 0 or 1. So in this case, let's put 0 to be safe. So LD2 must be 0, LD3 must be 0, and another one is SEL2. Because this is 2-bit, this is 2-bit, so it is 0, 0 for S0. And when we go to S1, what we want to do is rack 1, we want to transfer the data from rack 1 into rack 2. So what we need to do is the data from rack 1, which is here, need to be available on this bus, and of course we need to set SEL2 to be 0, 0, and in this case SEL2 must be 0, 0, must be, yeah, cannot be 0, 1, 1, 0 or 1, 1. And SEL1 actually is don't care, you can put 1 or 0, but in this case we have 0 because we don't want any data from here, right? SEL1 is 0, LD2 because we want to have the data to LD rack 2, so LD2 must be 1. So here LD2 must be 1, and what about LD1? LD1 is don't care, LD1 you put 0, LD3 we don't use yet, so LD3 must be 0 also, right? But these two is the one that we need to make sure that this one is 0 0, and LD2 must be 1. For here, this one must be 1, this one must be 1. What about the last state? So the last state will be rack 2 is transferred to rack 3. So rack 2, to transfer rack 2, what is inside rack 2 to rack 3? The data must go through this and here. So SEL2 must be 0 1. So this is important. SEL2 must be 0 1. And LD3 must be 1. LD3 must be 1. The others we can set to 0. And should be done here, right? So remember, when we design the finite state machine, so if this is the output and this is the output at every state, so we can have the finite state machine, right? So our finite state machine will be, or it looks like this, and this is a more state machine, right? The output, all of these are actually inside this state, yeah. Because there are many signals, so I write here, but it is actually in this. So if this is our state diagram, so we can now derive the functional block diagram of our FSM, which is this. Remember, again, we have the flip-flops, or in our case, register, and we have the output logic, and we have the next state logic, and of course we need to have the feedback. This is a mask, this is output, this is next state, and how many bit is this line? How many bit? We have 3 states, so 2 bit is enough. This is 2 bit, and of course our output is SEL1, LD LD1, LD2, LD3, we have SEL2 bit number 1, SEL2 bit number 0, because SEL2 is 2 bit. Right, so this is our finite state machine, and if we have this, actually we can create the Verilog code already, right? So for the RTL design methodology, the state diagram also we can represent in the form of what we call the control sequence table, or RTL, control sequence table. So this is actually uh, represent the state diagram and also the activated signal here. So we can see that in here, yeah, state 0, what we do that these are the signal that are activated LD1 SEL1. So LD1 SEL1, and it is 1 SEL1, and the others are 0. All right. And for state 1, signal that are activated is this LD2, and SEL2, bit number 1 and bit number 0, both are 0. So both are 0. We can write like this: SEL2, bit number 1, asterisk here means that this is uh, active low or a low logic low. All right. So both are logic low. So LD2 must be 1 and this 2 must be low. So this is exactly this. And the last one is this. And these are the activated signal. LD3 must be 1 and this one must be 0. This one must be 1. So this is exactly this, and this is the things, right? And we can have the CU. This is our CU, and this is our code. And again, I will show you how to write the code for the control unit, or to create the FSM. So this is exactly what we have. Yeah, we have the 2-bit for the next state and state logic, and we have the, here we call it control signal. Yeah, we group this together and name this as a control vector. All right, and this is a 6-bit 520. And let's see how to create this finite state machine. So again, in our Verilog quarters, we create a new file. And actually this one we need to have the another folder. We call it and this is a control unit. We call it CU. And the name is this. And we don't want to attach any file yet because this is only CU. So again, I use the device that we have in the lab. Finish here and Verilog. Okay, so let's write the code. So the code will be based on this, and also will be based on this. And again, this is actually not that difficult if we know how to uh, describe the finite state machine that we have learned in chapter 4 actually. So let's start. Module. The name of our module is this. And we have, again, the clock. This, the clock. And the reset also, we need to have that. Yeah, because our finite is finite state machine is based on this, and we have reset to go to the first state, and we have uh, clock reset, and what else? We don't have anything here, so we can have the output, and the output is actually name we in the slide we use we use the LD. The CV is for this, so because we want to integrate or connect to the DU part, so we use this. We have SEL1, we have SEL2, we have LD1, we have LD2, we have LD3, right? That's it. And what about our input? Our input, we have clock, select one, select one, select two is 2-bit, so we will have another one. We have LD1, LD2, and LD3. We have 2-bit input. Oh, sorry, this is not the input. Yeah, sorry for that. This should be the output here. So input, we have only clock and reset, and this should be output. SEL1, everything here are the output. SEL2 is 1-bit. SEL2 is 2-bit output, and this should be rect data type as well, because we will describe using behavioral modeling. So of course it will be in the always block. Okay, so and again we need to have the state name, so we define using a parameter declaration. So, and this is 2-bit, and we forgot another two signal, which is the next state signal, or you can use Y, capital Y, or small y here. So in this case we need to declare as rect, and this is 2-bit. First one is the next state logic, and also the state logic. This is next state, this is the state, and the name for the state as 0 equal to 0, as 1 equal to 1, as 2 equal to 2, and should be done here. And now we want to define the state register. So this is state register, and to define state register is easy. We use always block, and now is this negative h. I will explain later on why we use negative h here, but in the data path we use positive h. Yeah, see here we use positive h, but here we use negative h. This is we have a reason for that. Yeah, this is not not uh, uh, just only set now whether it is positive or negative, but we have a reason to do that. So in this case, we use negative h, so neg h clock, and the positive, the reset will be positive or active high should be the same. We cannot be the reset cannot be different, because if different, this circuit will not work, because if this one not reset, the other one will reset. So this is wrong. So the circuit must be reset at the same for the same time, at the same time. So if reset is activated, so the output of the flip-flops or the register here, which is the state here, must be equal to 0, or here state 0 in this case. Else, if not reset, the output of the flip-flop here must be equal to the next state. So that will be the state register, which is straightforward. Now the a little bit difficult one, which is this one and this one, yeah, to define this and this. This is actually not that difficult, because we can use behavioral code, right? So this is called the next state and output logic, and of course we need to use the always block, and it is sensitive to only one signal, which is the state. This one sensitive to this one also sensitive to this. So we have state, and we can use case statement, because we can have uh, many states, right? So either state 0, state 1, or state 2. So we can use case statement. So for state 0, at 0, we can have begin, because we will have many statements in the state 0. So first, in state 0, the output, yeah, the output we can use this. So this is the state 0. So the output will be we because we use CV, or we can write like this, LD1 equal to 1, LD2 equal to 0, or we can have another signal called CV, where the CV is in the rect data type, and it is 5-bit CV, 5-bit CV, where we can use that CV should be equal to this, yeah, 5-bit 6-bit binary 100 100 100 and of course in S0 also we need to define the next state that we need to go, and to go to next state we will not depend on any signal, so we don't have the input for the finite state machine, so the next state will be always S1. And remember, because this is a combinational circuit, you see, we use the equal sign here. Equal sign here. right? So that will be the first state, and the second state will be this. You can copy and paste and change this to 1, and the output exactly will follow this, which is 0, 1, 0, 0, 0, 0. And the next state, of course, will be S2, and next one will be S2, and this will be follow this 0, 0, 1, 0, 0, 1. And next state we can go back to state 0. All right, in the hardware we need to go back to state 0, and because we have 2-bit, yeah, the size of the state is 2-bit, or we have 2 flip-flops, so we need to define all the possibilities. So the last one will be this default. We can use this, all are 0, right? All are 0, and next state is 0, or you can use don't care. It doesn't matter. And in case means that finished. Now because we have this SEL 1, SEL2, LD1, LD2, LD3. So now we need to connect the CV signal into to the correct signal for the output. So we can here, all right, because we use TV here, so but the output port is used this name, so we need to have LD use assign keyword assign LD1 is actually this one is LD1, right? This is LD1, so this is actually CV5, and the rest we can actually copy and change the value. We have LD2, which is this one. This is number 5, number 4, LD3, number 3. We have SEL 1. This is CV2. We have SEL2, another one also SEL2, but this is bit number 1. This is bit number 0, and this is 1. This is 0. Done. Right, so this is our code for the finite state machine that exactly represent this and based on this behavior. Now we save our design, save, and we have this, save, and we try to synthesize and see what happened. Oh, we have error, 6 error, and yeah, it's a syntax error, so it should be okay. Let's look at the error. The error is here. Or we need to have, or we forgot the comma here between this and this. And what about this? This we forgot to have the semicolon. What about this? This should be Always, yes, we don't have this. What about this? S1 is already declared in the present scope. S1, maybe this one is 0 S1, S2, S1, S0, S1, S2, S1, S2, S0. Should be okay. Maybe the previous one. So just again, you have object LD1 on the left hand side of the assignment must have net type. So LD1, LD2. Oh, here no need to have rect, right? Because we use data flow modeling in this case. This is data flow modeling, so no need to have rect type. Should be okay for that. Yeah. Now we have 3 warning, but we don't have any error now. But we should check that warning because sometimes it will give problem to us. Yeah. It may be the design issue, the connection issue. No error means there is no any syntax error, but we might have connection problem, and normally it will uh, give you in the form of warning like this. So we need to check the warning. What is the warning? And of course, the first one is the license warning, but this one output pin are stuck at VCC or ground GND. So we need to check. It says that SEL2 bit number 1 is stuck at 0. What is stuck at 0? Stuck at 0 means it's always 0. No matter you do, means that every time this signal is always 0. So we need to check SEL2. We need to check our specification. So SEL2, let's look at this. SEL2 bit number 1. So which is this one? Is it stuck at 0? Yes, our design specification state that this one always 0 because there is uh, no occasion that we will use this one or set this one to 1. In our case, it's always 0. Means that this warning is okay. That is our intention. We want to have the output be like this, then this one should be okay. But if you check, for example, in your SEL2, you are not always 0 like this. For example, here you have 1, but you have this, means that somewhere in your code is wrong. Maybe here you have, you put the wrong value here, then you need to check, right? In our case, it is okay. So done in our FSM. Now what we want to do is to combine these two, right? Because remember that right here. So remember that the complete system will be here. Yeah, we need to have CU connected to the DU, and we have DU already, and we also have CU. Now we want to connect that two such that we have this. All right. So to connect both is actually very easy because we have these two already, and we have learned already how to design another module, another circuit, a bigger circuit that will use these two modules, which is the hierarchical design methodology. All right. So how to do that? So we can create a new one. Then close this, you create a new one. And of course, you need to have a new folder. Let's name it. Name this as DUCU integration. And the name is this. And here, add file. So now we have file, or we have the previous design that we want to use. Yeah. So we need to add. So the first one is of course the CU one that we have designed just now. Add. And the second one that we want to use is the this one, the DU. Add. And yes, next. And this is just the setting. Select the one. Okay, so the Verilog, create the Verilog file. Okay, now module, file name, and the port. So the port now is, if we look at the design, here is the design. Okay, the port now is clock, reset, data in, data out. These are not the port anymore, but it's a uh, a wire that connect this module to this module. So you will have clock, you will have reset, and you will have data in, and you will have data out. Done. So your input will be clock, will be reset, your output will be you have another one input, which is the 4-bit data in. You have the output, which is the data 4-bit data out, and you have wire, of course, which is the all the control signal, the LD1, LD2, LD3, and SEL1, 1-bit, and you have also wire, which is 2-bit, SEL2. Right, done for all the wire and the input output. And now we want to instantiate the module. So remember, to instantiate the module, of course, we need to have the name of our module. So we can open the name of the module. So the first one is of course this one, right? This one, and we need this, and let's name this as data path. Okay, you can name anything here, but make sure that the name here is this. Name this module, and the port list. You want to connect the port, and because we use the same name, so we can copy this one and put here, right? Such that the arrangement is the same with the one that we have here. And another one is the CU, so we need that. this one, CU. So the name is this. So we can just copy. And here we now call this as maybe control. And what is inside is this. And we can just copy and paste. Now we can have these two instantiated in this and done. All are connected. So we can end module. So this will represent this. All right, you see what we have learned previously in chapter 2, chapter 3, right? Where we use the hierarchical design methodology to instantiate or to use to reuse the previous design, which is this one, to create this one, right? So now we save. I cannot press save here because it's okay. It actually can save, but make sure that the folder is the correct one. Yeah, because the quarters normally if you uh, press save for the first time, it will save at the last file, the last file that you open. So make sure that this is in the correct folder, which is this one. Save. And now you can synthesize. And we have 10 warning. Because of the three-state buffer that we have here. So actually this one is no problem. If you change to this, it should be okay. Yeah, now you don't have any warning. Yeah, only one warning with the license and the other okay, right? So this is the data path, and of course you need to write the uh, detachment. Okay, but we are at 5 already, so I will share with you the detachment so that you can test on your own and see the result. So the result will be something like this. Yeah, when we have this and we write the attachment, and in the attachment when we simulate, for example, this is our attachment. We have the clock here, we have the reset, and initially data in is 9. Yeah, at the first cycle or first state, this is the state 0. So we load the data into rack 1. So this is how the data is from data in go into rack 1, and next state as 1, we load again or we transfer the data from rack 1 into rack 2. So we can see that number 9 here, go to here, we have number 9 also, rack 2, and the next one, state number 2 or S2, the data from rack 2 now go to rack 3, here. This is exactly what we want. Data in go to rack 1 S0, rack 1 go to rack 2 S1, rack 2 go to S3 S2. Exactly. And you see, we repeat the operation. Now we change the data at data in, and we can see that data in here will go to rack 1 at first as 0, and go to rack 2 as 1, and go to rack 3 as 2. And also again, when you change to A, you can see that you can have this thing already. So this means that our design is correct based on what we want the output here, right? So hope you can understand that this CU will generate the control signal. This is the control signal that will control the signal here. These are the control signal to sequence the operation of the movement of the data here, right? So it is very important. And this is the process of designing this uh, kind of digital system, or we can call it a complete digital system, where it can perform what we want the circuit to do. Okay, so I think that uh, will be the lecture for this week. And next week we will continue with look at the design flow. Actually, we have covered the design flow already. This is the design flow already, but we will look at uh, the detail of the design flow, what we do first and next, and so on and so forth. And we will look at the example 5.2 and try to look at the exercise also. And we should be able to finish chapter 5 by next week. And remember, you have one tutorial question to do and submit before our class next week. Okay, so I think that will be the class today, and I will share with you the code for the uh, test bed for you to simulate. And one more thing is that uh, actually, if you use this code, yeah, and you try to simulate later on, you will not get the result that you want, because here we don't have any output that uh, this one. Here we don't have any output that is connected to the register. So actually, we cannot see the content of the register, except that we have the signal tab, yeah, to this register, and we declare that as the output. For example, here the complete code is this. Yeah, I show you. We can we? Yeah, I got question from is how to spell your name. Is we is it correct? Sorry for that.
Aishwarya, Doctor.
Yeah. So yeah, I will answer your question later. I want to share this first. All right, is that okay? We are now at 5059, another 5 minutes, or not more than 10 minutes. Is that okay for you? So I want to,
Yeah.
yeah. So I want to share with
Okay,
you
Doctor.
the code that allow you to see the output like this. The output that we have in the simulation like this. Yeah, REG1, REG2, REG3. Because in the code here, we don't have any output for rack 1, rack 2, rack 3. Actually, in the simulation, you will not see that if you don't have any output that connected to that. So what you can do is this. In your code, you have this rack 1, rack 2, rack 3 for your output as well. And here, as instead of declaring the rack 1, rack 2, rack 3 as the output, as a rack only, but you have output here. Only then you can see the output. And also for for the CU, when you want to see the uh, state, so you need to have the state just like what you did in your assignment, and you need to have the state listed in your output, and here the state must be declared as the output. Only then you can see the state like this. Here the state. Okay, that is how. So I will share the complete code with you so that you can try on your own, right? Plus the attachment. Now come to the question why we use neg h at the CU module. Here negative h, but here is positive h. The reason is that we want to have, or we want to change the state before we load the data into the register. So we can see that here, especially here, right? The state change at the negative h, right? This is negative h, negative, negative. So it will change from S0 to S1 at the negative h, all right? So we want the data to be read or to be transferred at the middle of the state here. So because we set this as a positive clock h, means that the data will be transferred at the positive h here. So you can see that, see, because this is negative h, the data is not transferred yet. It is transferred at the positive h here. So the data from here, from here, from here, rack 1 will go to rack 2 at exactly at the middle of the state. Why we want that? Because we want to, or we want our circuit to be stable first before the data can be transferred. So it is not good if, for example, we have something like this. This is not good when we change from example S2, S0, and then we change to S1, and we read the data or we transfer the data here. So this is rack 2, for example, this is rack 1. So we want to change we want to read the data at the same time when the state is changed, when we change the state. This is not good because actually if in practice the register need some time to be stable. We call it setup time. We are from state 0 to S1. This is undefined part actually, and this is dangerous. All right, so what we want to do is we want to be stable first. Make sure that, yeah, we are in state S1 and we transfer. So this will make sure that the data, everything is good, is correct. All right, that is the reason. Yeah, see here, exactly in the middle, here, exactly in the middle. Right here, no problem because we S0 and is actually inside. Yeah, the data is inside the state. Okay, so that is the reason. All right, so I think done today. Any other question?
No, doctor.
No, doctor.
Okay, so if no question, we will end our session here. Thank you very much. See you next week. Goodbye.